Hey there, it's Charlie from Brooklyn Bridge Ventures, and we're here to present another lunchtime stack-up. This time it is around engineering and data science, and we have Justin from Instnt who is going to come up, and he's going to share a little bit more about operationalizing some of the predictive models that they have going on. So as soon as Justin comes up and turns on his camera for the presentation, I will hop out of his way. Awesome. Justin, thanks for joining us. And your mic on. Awesome. And then you should have a share button down at the bottom for your presentation as well.
Okay, so I just share and take it away?
Yeah, sure.
Okay, I'll introduce myself. Okay.
That is artistic.
Yeah, that was unexpected. Present. Start from the beginning. All right, do you see that?
That works great.
Okay. Anyway, like Charlie said, I'm Justin Kamerman, Chief Product Officer at Instnt. We're a startup based in New York City, building identity verification and fraud detection software. Anyway, this presentation comes out of sort of my experience over the years working with integrating data science and machine learning into products. I think the case study is most relevant to Instnt, but I think applies quite broadly in a general sense. So hopefully you can all get some benefit out of our lessons, which are mostly learned in the School of Hard Knocks. Yeah, so just Instnt, it's the first fully managed customer onboarding platform for business with fraud loss insurance of up to $100 million annually. So there's a lot of other businesses out there offering fraud detection. Sort of our big differentiator is that it's a fully managed service. You don't really have to worry about integrating vendors, decision rules, models, etc. And then there's the really unique feature of it, which is the indemnification. Because we control so much of the platform, we're able to take out insurance against fraud loss. So yeah, like I said, our differentiator is how easy it is to integrate. You just log into our dashboard, you answer some simple questions as to what features you want, KYC, OTP, biometrics, device fingerprinting, etc. And then we have some simple APIs, which are for integrating on mobile, on web. And so we really push to try to make it developer friendly, nice and easy to be the Stripe of onboarding, so to speak. Anyway, so to get rolling about where data science is involved with engineering, this tends to be most acute that these two sides work together properly. In a company that's producing a product where the product directly involves some sort of data science, predictive capacity, or model. There's other businesses where the data science work products are sort of used internally, but I think the need to collaborate in a productive manner is most acute when you're actually producing a product where outputs from engineering and data science actually get deployed and used and are both sort of affected by the constraints on one side and the other. So anyway, I'm sure you've all seen Drew Conway's, I think he was from, well, I'm not even going to embarrass myself to say where he used to work, but anyway, he's well known for sort of defining this Venn diagram to summarize the skills that go into creating the perfect data scientist. Well, not even the perfect one, but just shows the sort of relative blend of skills and sort of where you sort of tend to operate with your blend of skills. So there's the computer science and software engineering, the quantitative side with math and statistics, and then there's always domain expertise. So at Instnt, the domain expertise would come in with compliance, identity verification, KYC and things like that. The math and statistics, that's on the data science side, building predictive models for fraud detection, identity verification, feature engineering, especially from customer data, or sorry, from vendor data. And then on the computer science side, because you're building a hosted service, potentially multi-tenant, there are all the engineering constraints, the fun constraints to do with real-time latency, scaling, throughput, data protection, particularly when you're dealing with personal information. Data protection is quite. So anyway, we like to extend this diagram to, sorry, I jumped ahead there, to represent not the individual blend of skills, but an organizational blend of skills. So for us, sort of a continuum into integrating the engineering department, the data science department, and the domain expertise department. So the following slides are sort of all in that context, where these sides are all trying to work together to produce an end goal of a reliable, useful feature for the platform. So first of all, on the engineering side, the engineering workflow tends to be driven by some form of agile methodology. You work in sprints and deliver features either as time boxed or feature boxed. The day-to-day is dealing with from prototype to high scalability, parallel throughput. Are your databases fast enough? Are they big enough? Maintainability of code, code reviews, source control, things like Git, and now in Amazon code commit, we're controlling the quality of code that's going into delivery through code review of merge requests and things like that. And repeatability, it goes back to configuration management, where we're able to recreate any version or any configuration of the software for internal testing, recreation of customer issues, etc., and also for having sort of parallel development streams with prototypes, etc. On the engineering side, you're very much driven by the choice of language, programming language, that is, as to how a problem will be decomposed and how features will be implemented. Also very platform specific, on-prem, in the cloud, which cloud. In the beginning of the cloud, it was just lift and shift, where you took your code that ran on-prem and threw it up into the cloud. But now the clouds are becoming their own sort of particular flavor of implementing services. A good example is the Amazon serverless, which is sort of very specific to their platform, the Lambda Functions, API gateways, etc. So these choices sort of bind how we choose to solve problems, how we maintain our environment, and how we grow the product. Importantly, on the QA side, the testing tends to be testing for deterministic correctness. So that's a fancy way of saying we have some precondition A for a test, we conduct the test B, and we expect output C. And if result is not equal to C, then it's a bug. If it is C, then check, move on to the next one. So we'll compare this to in the data science environment, where QA is a bit more, has the sort of same principle, but the nuances are a bit subtle. So again, we're going for that perfect unicorn trifecta, where the code is deterministically correct. In other words, it doesn't have bugs, it's scalable and within budget. So we're all striving for these three. We usually end up being pulled in one or more directions more strongly. So compare that to the data science side, where the workflow is very different. It's by nature exploratory. You'll come up with a thesis or a hypothesis. We need to find data or mine existing data to support or invalidate that hypothesis. Sometimes the delivery criteria are very subjective. We don't know what we're able to achieve with the data. But I think it's very important to be able to quickly iterate and explore data. And it's equally important to be able to invalidate approaches as it is to validate them, and you eliminate dead ends, which can take up development time, and keep you on track of some part that will actually culminate in a final product. I know with academic papers, even a sort of invalidation result is a result, but here we're trying to stay on the path that leads to a viable deliverable product within the constraints. And also, it's great to say, well, we have a static data set and we validated our hypothesis, but this data is time sensitive, and we need to ensure that we can maintain the flow, keep this data current to support this being an ongoing value delivery. So once again, we're dealing with scalability, but in a slightly different aspect. Scalability might be to do with the data set size and the resources that are required to work with those. We may produce some very complex models which take a long time to generate a score, and we may make certain choices to gain efficiencies on that side, compromising accuracy for latency. Maintainability, similar to engineering, where we're wanting to make sure that data sets, the provenance of data sets is maintained. So if we have a model that's performing a certain way, we're able to work back from some sort of identifier to the artifacts that went into building that model, whether it's what data sets, what model was used, what hyperparameters, and what parameters were trained. So we need to be able to, and also this is important from a compliance perspective as well, to be able to show that you understand and have a repeatable record of what went into a particular model. So in this case, compared to engineering, language and platform, we're largely language and platform agnostic. Data scientists will typically do exploratory work in the tool of their choice in an environment of their choosing. They might use R or Python. They might use TensorFlow to train neural networks. But during the exploratory phase, they're generally just going to preferred tool or tool that supports the current sort of model type or algorithm that they're looking to exploit. At this point, when you're doing the exploratory phase, platform's not that specific or not that constraining. But as we move forward and as we sort of tighten up on our hypothesis and the sort of product, what's going to go into the product, and as the data sets get larger, we may be forced to deal with larger databases and specific tools that can handle the size of the data set. Like once we reach a certain size of data set, we might not be able to run models on our local workstation. We might have to use a MapReduce cluster or a Spark cluster or a big Redshift database. So at that point, there are engineering limitations that come into play. And here on the QA side, compared to engineering, on the engineering side, we tested for deterministic correctness. Here we're looking at the law of large numbers, which you run tests a large number of times because there's very often some random element. And we look for aggregate correctness. This is just because a lot of models are trained stochastically. Random trees, for instance, it'll randomly select feature sets. With neural nets, we'll randomly select the next example to stochastically upgrade the weights, etc. So once again, we're going for that trifecta, very similar in principle, within budget, low latency, and in this case, probabilistically correct. So the design on the QA side is quite important on the data science side. We've tried to reconcile these two differences in a way that, so the two sides have transparency and visibility into what each other is doing, but not to artificially constrain one or the other and force them to work in a sort of non-natural workflow. Although for certain deliverables, like if we're doing a new feature extract routine, we do need those two sides to interlock for release purposes. If we're bringing in a new feature, we'll need the data science routines as to how to extract that feature from the raw data. Specification of how that happens has to be fed into engineering. And then those two sides together have to deliver a scalable, latent, maintainable, and all those good things release with the sort of QA loop back where data science is able to validate. So the two sides generally at Instnt operate independently, but we try to interlock where there's dependence for delivery. And we usually track this through sort of our sprint planning tools, like we use Jira. Find it's really nice to also to use labels to separate out which falls on which side of the fence, and on tickets where those two sides both come into play for delivery. So we've also tried to build platforms where, because a lot of times I've seen in environments where data scientists, it's very difficult for them to access data. Generally nowadays, data scientists are pretty well versed in dealing with databases, etc. But if you have a data scientist who is a specialist in neural networks or graph databases, you're really not getting your money's worth if he's spending most of his day digging up data. So we try to create platforms where both data scientists and engineers can have rapid access to data, rapid access to tools, and the technical bar is very low. So someone who's, whether it's a time thing or a sort of technical skills thing, there's very few barriers to people playing around in the data. So what we've done specifically is try to create a common development environment for prototyping with common tools. We developed some internal tools where developers or data scientists will come up with some routines that they use personally in their own environment. Turns out if they are deemed to be generally applicable and might help other people from struggling to deal with, say, decryption of results, testing of an API, pulling data from a database, we'll wrap those into our internal Python module, which we have, which is loaded up into this shared development environment, which is actually a Jupyter Hub server, which runs inside our cloud. So it has direct access through security rules into the database, compared to if you're accessing the database locally, where you have to set up tunnels, etc., to get through to the VPC. We love tools like Bardo to access the Lambda services, S3 services. So it's easy for data scientists to prototype by looping in existing Lambda functions in our stack and using those directly in the notebooks to prototype. Also, the Jupyter Hub notebook, although it's built sort of a descendant of the IPython, Python-specific stack, it's a very versatile, pluggable kernel structure that gives us a broad breadth in terms of tools that we use. We can use languages like R, Julia, JavaScript, etc., all in addition to Python. But we also, for model training, we use the H2O cluster, which has some really nice client libraries, which we can just drop into the notebook. We can leverage the training cluster directly from the notebook, whether it's in R or Python, for training and analysis. And then once models are trained, we can serialize those as Java classes. And here's a nice handoff to engineering, where you say, well, here's a Java class, and on the engineering side, we have a sort of a Lambda function that will take these mojos or pojos that are serialized from H2O, read the metadata from the zip bundle that's produced, and deploy the model. So the pathway from developed model to in production is very quick. Also, we love dashboards. We like to build dashboards quickly to monitor operations, to do troubleshooting, debugging. If there's dashboards that we think are sort of generally applicable to customers or for internal administrative interfaces, we can bubble these up and they make their way into the product. But there's a very nice sort of workflow of rapidly prototyping dashboards and just throwing them away when you're done, because it's relatively easy. And we use things like Grafana, Shiny, and R, and then IPy widgets. But we can leverage all these lower level tool libraries to quickly get access to data in a safe way. Just checking the time here. Anyway, like I said, our development environment, we love Jupyter Hub. We can leverage multi-factor authentication. So it's a nice secure environment controlled by access to our G Suite accounts. Like I said, pluggable kernels for Python, R, Julia, etc. And from here, if you're writing functions, it's a natural transfer of well-structured functions that really have no side effects other than interacting with Amazon services. It's a nice, smooth transition for engineers to implement those as fully baked Lambda functions in our stack, or even some of our data scientists are quite comfortable doing that at this point. Model building, like I said, we like H2O. Have used DataRobot in the past. DataRobot tends to favor environments where it is a sort of monolith where training and prediction happen in the same stack. in a high throughput environment, we tend to prefer H2O since the trained models are serialized as Java, and there's a very clean break and a very clear separation between training environment and production. But both great platforms. Just our use case, we've really enjoyed using the H2O and the tools that provides, and it integrates really nicely with the notebooks as well. Like I said, dashboards. We love dashboards. We use Grafana and go straight to the database. For something more sophisticated, we'd use things like Shiny and IPy widgets. Like I said, these can be whipped up pretty quickly. They look sort of borderline slick and can be thrown away once they've served their purpose, or if you just want to start up again. And then, like I said, the models are deployed very quickly as they sort of wrapped up inside Lambda functions. Once they're deployed as Lambda functions, we have all the great tools that come with that. So we really like the X-ray functions in AWS can break down exactly where the latency is occurring, how many calls were made, errors, etc. So this is sort of a snapshot of our sort of web of Lambda functions from customer requests through API gateway to, and you can highlight specific areas. This would be a model, a predictive Lambda function. So we can look at latency. So it transitions very nicely from a data science specific artifact to something that engineering can operationalize and monitor just like any other engineering component without having to write a lot of code not a lot of overhead to operationalize it to this level. Anyway, that's sort of our approach at Instnt. Like I said, these two sides, engineering, data science, need to be able to sort of follow their own flow. But really, if you're delivering a product that relies heavily on both of those components, you need a way to rigorously interlock them for deliveries on schedule, performance, and quality control as well. That's it.
Thank you very much. I have a quick question about just like context. Right now, like how big are the teams and how long have you been working on this? And I wonder if you can sort of talk about, like, is this the setup that you started out with, or did you start with something that was sort of a little simpler and kind of build up to this? Because a lot of the folks are maybe just starting their implementations and they're wondering sort of how much time, effort, work, and people went into what you have now.
Typically just incrementally. Instnt's been around for 2 years now. It started off, a couple of engineers and a data scientist, and then the sort of management staff. So usually in the beginning, and I'm basing my experience on Instnt plus a couple of other companies where we're building services using machine learning. Data scientists tend to sort of start off in a corner with a data dump or data file. Then after a couple of months, the prototyping, the engineers will start building out sort of the basis of a platform. The data scientists will start to build out the basis of some hypotheses and start to validate and invalidate them with models. But very quickly, the question comes together: how do we sort of integrate the model into that? And that's where you can look for a data scientist who doesn't code at all, and there's nothing wrong with that. And if that's the case, then engineering sort of has to lean over that way and sort of say, okay, what do you got? You've got an R model, so how are we gonna get that into production? Are we gonna transpose that into another language? Like I said, H2O, we like H2O because we can just point a data scientist at H2O, and when he says, yeah, I got a model, it looks great, we can just say, well, give us the Java file, and then that goes over to engineering. So and then the tools have just sort of grown organically. I think building up a shared development environment that's sort of based on something like Jupyter Hub is a great first step because it's a very general environment. Engineers and data scientists can use it alike even before they're collaborating. Once they start to collaborate, you have a shared file system. The nice thing is, it's great. Everyone's setting up their own environment locally, and then you install a version of NumPy, and it's not the same version as someone else, and then the code doesn't work and you lose time iterating on that. In this shared environment, the modules are all shared, so you're all in the same version. It's a pretty seamless back and forth. And then from there, you just sort of build out the teams. Engineering sees a need to build out the UI, so we'll hire some UI developers. There's a need to operationalize more models, so you'll end up with a back-end developer doing work with Lambda and the H2O models. Data science, growing that up right now, but it's nice to have things in place with a small team, and then when others join, they fit into this structure. Once you've got a lot of people, you have as many people as you have, you potentially have different ways of doing things, and then you've got to sort of struggle to converge. I think it's really nice, even if you just have a team of 2 or 3 on the technical side, to start putting these tools together, even if they're not perfectly integrated, but at least have the basis of something that new people can come up and say, hey, here's your account on the shared environment. Here's where you can prototype dashboards. Here's the S3 bucket that we put trained models, etc., and we go from there.
One other question I have before we go about team and recruiting. A lot of the folks that are out there who have done a lot of data science work may not have come from commercial or startup environments. And as you have sort of added folks on the team, maybe folks who have like academic backgrounds or coming from other spaces that aren't necessarily used to, kind of a startup environment. Do you have any thoughts on sort of how you either filter for the right kinds of people to work on a data team, or B, just how to onboard them and set expectations, set a culture of the right kind of collaboration and all of that kind of stuff?
Yeah, like I said, like access to data is kind of key. You get data scientists that sort of sits right in the middle between engineering and sort of extreme quantitative side of things on the data science end, and they're able to write some code and do some modeling. And those people are very versatile and usually great in a startup because of everyone's sort of multi-taught or spread across a broad spectrum of competencies. As you become more specialized, you might say, well, we need to build a neural network. We need to know someone who knows TensorFlow. So it makes recruitment difficult if you say, well, we need an expert in TensorFlow or graph databases, but then they also need to know all this other stuff. So it really shortens that list. So having these tools in place that lower the technical burden for saying, here's a notebook to pull last month's data, just run the cells, you've got the data, and then use your favorite modeling tool. It's a very quick onboarding, coming up to speed process, as opposed to like, ask the DBA to create your an account, set up a SQL client, go connect to the database, run some SQL, don't delete anything, and go from there. So yeah, you kind of need to, like I said, the versatile personalities are great, especially in a startup, but you also need to accommodate with his highly specialized, like a UX, UI, Angular developer. He needs to be able to operate productively in that environment. And equally true of a data science specialist on, say, graph databases, semantic databases, or neural networks.
Gotcha. Cool. And do you currently have positions on the team open?
Yes, we do. We're actively hiring. You'd have to go to our website. Sorry, I didn't put that up in a slide, but it's just instant.org, instnt.org. Yeah, we're growing, we're hiring, and yeah, in a startup, it's after your initial sort of prototype is up and you start to bring customers on board, each hire is quite strategic. I like to think the environment we've created is sort of removed some of the must-have skills, and you can sort of go a little deeper into other aspects because they don't have to know everything under the sun in order to be productive in the environment.
Gotcha. Well, listen, thanks so much for spending time with us today and giving us a look under the hood on what you're working on and making our lunch today educational. Really, really appreciate it.
Thanks for having me. It's been great.
No problem.